Let's go ahead and get started this afternoon. It's my pleasure to welcome you all to the University of Washington's Astrobiology seminar for today, and it's my privilege to introduce Professor Rajdeep Dasgupta today, who will be our speaker. So before we get started, I just wanted to introduce him a little bit, and then we'll pass it over to him to give his presentation. So Raj got started in his academic career at the University of Jodhpur in India, where he got his bachelor's degree and master's degree. He then went to the complete opposite side of the world to the University of Minnesota, where he got his PhD. He stayed there for a couple extra years as a postdoc before jumping over to Columbia for a second postdoc, and then arrived at Rice University for a professorship, which is where he still is today. Raj is an expert on interiors of planets, both in our solar system and beyond. And he is also the PI of one of the large Nexus collaborations, the Clever Planets group. So today, he will be presenting his research on volatiles, life-bearing volatiles that are important for life in the formation and evolution of planets. So when he presents, what I'm going to ask all of you to do, please, is to mute your microphones and to stop your videos so that he can have all of the bandwidth. If during the seminar, though, you have a question, feel free to either type it in the chat room, raise your virtual hand, or even just interrupt Raj. He said that that's okay. So with that, I think I'm going to turn it over to Raj to give us today's presentation. Please take it away, sir.
Thanks, Rory, and thanks everybody who took the time today to meet with me. I had a wonderful virtual visit so far. And let me see if I can share my screen. Can you guys all see the screen fine?
Yes, we can. Looks great.
Awesome. Awesome. So again, thanks for having me visit you guys virtually for this wonderful astrobiology colloquium series that you guys have. Today, what I'm going to do is to talk about the fate of life essential volatile elements during formation and differentiation of rocky planets. And specifically, I'll kind of focus on the origin and the fate of life essential elements in the context of our own solar system and specifically for our own planet. This is basically a collaborative work that is otherwise not going to be possible without a lot of hard work done by many of my former students and current students and postdocs. I want to acknowledge them, of course. This work would also not be possible over the years by funding of various funding agencies, including the David Lucille and Packard Foundation, Deep Carbon Observatory, Sloan Foundation, and of course, NASA, and currently the wonderful research coordination network, Nexus, that I'm pleased to be part of. Many of the ideas kind of evolved through many of the dialogues over there. And as Rory mentioned, this research that I'll present today is actually one of the components of our interdisciplinary initiative called Clever Planets, which stands for Cycles of Life Essential Volatile Elements in Rocky Planets. That's one of the teams within Nexus, funded by NASA. So I have been fortunate to work with many students and postdocs over the years, and specifically the talk I'm going to give today involves many of the work that's getting currently done by current student Daman Grewal. It also would involve some of the work my former postdoc Yuan Lee did with me, my former student Megan Duncan, who is now an assistant professor at Virginia Tech, did with me, some of the work that James Eguchi did, who is currently a postdoc with Tim Lyons' group at UC Riverside. So again, basically, it's not just my work. Many of the work that these guys are doing or have done, I'm sort of going to do to a best job in presenting them today. So again, the thrust is origin of carbon, nitrogen, hydrogen, sulfur in rocky reservoirs, and we are going to make the point that the origin of these volatile elements in rocky portions of inner solar system planets is a key step towards building a habitable world. The reason we are focusing on the rocky reservoirs of these planets is the surface of our planets and the rocky portions of these inner solar system planets are in constant communication. Magmatism and volcanism in places like mid-oceanic ridges and hotspots in our planets releases life essential gases to the surface, whereas subduction or other modes of recycling sometimes sequestered them into the interior. But over long time scales, the surface and the rocky reservoirs of our planets are constantly in communication. So in order to understand the surface habitability of the planet, we not only need to understand what's the budgets of these life essential elements on the surface, but we also want to know what's the budgets and concentrations and the evolutionary history of these important life essential volatiles in the entire rocky reservoir of our planet. So the crust, the mantle, and the atmosphere, hydrosphere all together. So if you are paying attention to all the questions related to astrobiology and origin of life and so on, there are sort of two main modes of thoughts that go into this. One is delivery of organic molecules of prebiotic significance as a direct molecule as precursor of life. The other aspect is thinking about the origin of these life essential elements as a whole, not necessarily as the molecules of prebiotic significance, but then processing them through some endogenic planetary processes so that they can evolve towards necessary organic molecules. So the overall emphasis in our Clever Planets initiative is sort of falling on the latter category. So we are interested not directly about origin of organic molecules of prebiotic significance, but we are interested in the origin of the elements that are essential for forming those organic molecules. So again, the reason we are interested in tracking life essential elements through the whole planet scale process and thinking about the origin in the whole silicate reservoir, the non-metallic reservoir of our planet or any other rocky planets, is the fact that when you think about any life essential volatile elements, such as carbon in this particular case in this slide, carbon cycles between the near surface reservoirs of our planet, between hydrosphere, biosphere, atmosphere, and so on, in a relatively rapid timescales. They transport in the order of sort of 100 to 1,000 year timescales. As you look at the fluxes in terms of 10 to the power 14 grams of carbon per year, and the reservoirs that are in the order of 10 to the power 17 grams of carbon, if you do the ratio of the two, you get the residence time of carbon in these near surface reservoir for our planet, and they are in the order of 100 to 1,000 years. On the other hand, if you look at the best estimates that are out there, there are a few studies like this one that try to estimate the carbon budget and the fluxes between different reservoirs, not just thinking the near surface reservoirs, but as well as the mantle and the crust and so on. You will get the fluxes that are similar order, sort of 10 to the power 13, 10 to the power 14 grams of carbon per year of fluxes, but the reservoir sizes that we are now talking about is much larger. They are in the order of 10 to the power 22, 10 to the power 23 grams of carbon, right? So if you do the ratio of the fluxes and the reservoir size for this whole planet scale carbon cycle box model, you will end up getting residence times that are on the order of billion years, or at least tens of millions of years, right? So over a long time period, over giga-year time period of evolution of a rocky planet and the surface habitability, you need to be thinking about the exchange as well as the budget of elements such as carbon and nitrogen and sulfur, not just at the surface, but as well as at least in the silicate portions of the interior. So again, because of that, our focus here will be the origin of life essential elements in the BAC, or the bulk silicate Earth, right? So if we are focusing on our own planet, we are going to be interested in the origin of these elements in the exosphere, the mantle all together, which we are going to call bulk silicate Earth, okay? And because that's going to matter for long-term climate and habitability of the planet. So what do we know in terms of the source of life essential volatile elements for our planets? The sort of the current paradigm, if we will, is that the volatiles are delivered to our planet through chondritic meteorites that come from the asteroid belt, right? These are the building blocks of the inner solar system planets as we know them. And the current thoughts are that these meteorites are kind of right type of building blocks that can also deliver life essential volatile elements. What are some of the arguments in favor of that? One of the key arguments in favor of the origin of volatiles coming from these carbonaceous chondrite type of meteorite in particular is through looking at volatile element stable isotopes. So here I'm showing a plot of nitrogen stable isotopes plotted against delta D or deuterium to hydrogen ratio, the sort of stable isotopes of hydrogen. And what's plotted here is the estimate for the bulk silicate earth in the star. And all these triangles and the squares are basically estimates for different carbonaceous chondrites, ordinary chondrites, instaite chondrites, and so on. And what you can see is there is actually a fairly good match in terms of nitrogen isotope and hydrogen isotope composition of some groups of carbonaceous chondrites with that of the bulk silicate earth. So if you follow this sort of logic chain, it's pretty obvious to argue that late accretion of carbonaceous chondrite type of materials were responsible for delivering volatile elements to our planet. Because their isotopic compositions end up matching. If that is the case, the argument would be that the volatiles were delivered late into our planet after the major phase of planetary differentiation was over, meaning after the metal silicate separation, core formation, all of those were over, and there were some sprinkling of these late accreting materials that delivered the volatiles. But as it turns out, it's not so simple. Although the volatile element stable isotopes point towards carbonaceous chondrites being the chief delivery agents for volatiles, if you look at the nucleosynthetic anomalies for non-volatile elements, here I'm plotting sort of nucleosynthetic anomalies in titanium versus chromium and cap delta 17O versus chromium, you see that there are sort of two complete separations, like true dichotomy in terms of the carbonaceous chondrite group as well as the enstatite chondrite groups. And as it turns out, inner solar system planets, including our own planet Earth, actually ends up plotting or clustering towards the enstatite chondrite or non-carbonaceous chondrite type of affinity. So while the volatile elements can point towards carbonaceous chondrites as the chief building blocks for volatiles, the non-volatile stable isotopes point towards enstatite chondrites being the chief materials that made our planet. So clearly there is a debate in that sense. As it turns out that you don't even need to resort to these isotopes. Actually, if you plot the elemental abundances of some of the major volatiles like carbon, nitrogen, sulfur, or hydrogen. So what I'm plotting here is the abundance in the bulk silicate earth normalized by CI chondrite. What you can see is clearly these elements in the bulk silicate earth, as we estimated them over tens of years of hard work on igneous geochemistry and so on, that none of these elements are actually in chondritic abundances. Well, some are, but others are not. So we can expect these volatiles to be depleted in our planet, but if they were delivered chiefly by carbonaceous chondrite, we would expect all of these elements to plot on a horizontal line. They may be depleted, they may be lower than chondrite, but they will be all on a kind of like a horizontal line, meaning they will not be fractionated relative to one another. However, what we see in this plot is if you look at the carbon relative to nitrogen or nitrogen relative to sulfur or carbon relative to hydrogen, clearly they are not in chondritic ratios. Carbon to nitrogen ratio of bulk silicate earth is superchondritic. Carbon to sulfur ratio of bulk silicate earth is chondritic, and carbon to hydrogen ratio of bulk silicate earth is subchondritic. So if this is the case, late accretion of chondrites cannot actually explain the vast majority of the volatile abundance in our planet's degassable reservoir, meaning this mantle, crust, and atmospheric reservoir. We need to call for something else. Actually, recently, my current grad student, Daman Grewal, also led to a very interesting discovery from literature compilation of iron meteorite parent bodies. What we see in this particular plot is if you look at the carbonaceous affinity iron meteorites and non-carbonaceous affinity iron meteorites, there is actually a clear distinction in terms of nitrogen isotope compositions between the protoplanetary bodies that formed or served as parent bodies of iron meteorites of CC affinity versus NC affinity. And not only that, Earth or Earth's mantle and atmosphere altogether, it is actually right in the middle of the CC iron meteorite group and NC iron meteorite group in terms of nitrogen isotopes. So given the fact these iron meteorite parent bodies were one of the earliest formed protoplanets in the inner solar systems, which formed between sort of 0.3 to 1 million years within the formation of CAI or time zero, clearly there were already presence of nitrogen early on during the formation of these bodies. And more importantly, just the carbonaceous affinity iron meteorites do not end up matching with the composition of inner solar system planets such as Moon or Earth and so on. So we clearly need contributions from both. So given the fact volatiles seem to be around from very early on during the formation of planets, one thing that's pretty obvious is we not only need to focus on delivery of volatiles through undifferentiated meteorites, we need to focus on delivery of volatiles through bodies that themselves were already differentiated. Why I say that? The plot to the right shows the fractional mass in terms of growth of any given body with as plotted as a function of time after the solar system birth. What you see that many of these bodies, such as Vesta, Mars, they grew very, very quickly compared to a planet such as ours, which grew through collisional impacts and grew over a longer period of time. Given a planet like ours grew over a much longer period of time, the bodies that acted as seeds or building blocks to a large planet like ours, many of them would actually be things like Vesta or Mars-sized planetary embryo or planetesimals. But we know many of these bodies through geochemical studies, they are already differentiated. They had the core, they had the mantle, right? So in order for us to understand then the origin of volatiles in a planet such as ours, we not only need to think in terms of delivery by undifferentiated meteorites, but also delivery potentially by differentiated bodies, right? And if we then think about delivery by differentiated bodies, automatically another important regime where volatiles could behave in an interesting manner comes into picture, and that is what we call early planetary differentiation. So we talk a lot about planet formation and how volatiles were delivered to planet formation, but one aspect of planet formation typically is overlooked, and that is that planetary differentiation regime of planet formation. So the regime that we are talking about is where dusts and small rock pebbles, they're accreting, and as they're growing to hundreds of kilometers in diameter and so on, they automatically start to differentiate through internal heating by short-lived radionuclides such as aluminum-26 and accretional heats and so on. And accordingly, you can have fractionation of elements, major volatile elements between the magma, silicate magma ocean and proto-atmosphere, between the silicate magma ocean and the metallic core. As a consequence, now there is room for us to truly take into account if we want to understand how the silicate magma ocean and the proto-atmosphere, both of these reservoirs acquired their volatile budgets, we need to understand how these elements fractionated between the metals and the silicates, how they fractionated between the atmosphere and the silicates and so on. So the two sets of parameters we are focusing a lot on in our group to constrain these type of processes. One is the solubility of these important volatile elements in silicate magma ocean. Another is the partition coefficient of these volatile elements between the iron-rich alloy melt and the silicate melt, what I will refer to as simply as core-mantle partition coefficient or metal silicate partition coefficient. So through these parameter constraining, what we can do is try to address some of these key questions. Questions such as, what is the role of differentiation process in setting the distribution and inventory of major volatiles in rocky planets? How does the expected volatile fractionation vary as a function of conditions of differentiation, such as pressure and temperature conditions of differentiation, redox state of differentiation, composition of the planet or mantle of the planet, the style of accretion, and then what control does magma ocean differentiation condition have on setting the major element volatile chemistry of silicates and atmosphere? So, of course, these are very important questions in understanding the early evolution of habitability. The approach we are taking, there are many different approaches one can take to try to address these questions. The primary data sets we are trying to bring in addressing these questions are actually laboratory experiments. So, I am an experimental geochemist, a high temperature petrologist geochemist by training. So what we do in our lab is to simulate high temperature and pressure conditions of planetary differentiation in this case. So what we will try to show you is how we simulate in the lab very high temperature and pressures that would simulate a magma ocean conditions where metals and silicates are equilibrating in a molten state, and how we can use those experiments to figure out the nature of fractionation. So typically we will do experiments using piston cylinder multi-anvil these devices, and then once we generate samples, we need different microanalytical techniques to figure out the elemental fractionation, to put together a phase diagram, and so on and so forth. That's kind of our toolkit of primary toolkit that we will employ to get the data sets we need. So for this particular presentation, what we have been doing is we set out to do an experimental campaign of constraining, as I said, solubility and partitioning of major volatiles during early differentiation of rocky planets. So we have been doing experiments sort of simulating shallow to deep magma ocean conditions. So several gigapascals of pressure, several hundreds of degrees of temperature that we can subject these samples to. And by varying the chemistry, we can also vary the oxygen fugacity or the redox condition of this magma ocean processes anywhere between iron ooze type buffer, which is basically a redox condition where metallic iron and iron oxide, iron 2+ oxide will be in equilibrium. But we can also go to conditions that are much more reduced, so up to 8 log units more reduced than iron ooze type buffer, which would simulate core compositions that are deviating from pure iron chemistry, but maybe more silicon-rich chemistry, and so on and so forth. Once we do this chemistry, we need microanalysis like iron electron microprobe, SIMS, and then we can also do spectroscopy to figure out how the volatiles are dissolving in the silicates and so on. So these are some of the example backscattered electron images of typical experimental products we can generate. What you are looking here, you may not be familiar or you not be used to looking at this type of images. What you are seeing here is a silicate glass that is in equilibrium with a sulfur-free alloy, or you are also looking at another BSE image where quenched silicate melt is surrounding a blob of sulfur-bearing alloy. So what we can do, these products were once at a very high temperature and high pressure, but then we quickly cooled them so that we can freeze in the chemical information that was relevant at that pressure and temperature range. And then we will go in with any of these analytical techniques to figure out how much carbon is dissolved here in the silicate portion, how much carbon is dissolved here in the alloy portion, and so on and so forth. So going back to the main processes that I think we should be thinking in terms of the origin of the major volatiles on our own planet, it could be late veneer addition, that means post-dating core formation. It could be the atmospheric loss itself played a major role, or it could be core-mantle fractionation played an important role. Right at the bat, I would kind of rule out the late veneer addition being the main process. And it comes from one of the figures I showed you before, that the bulk silicate earth major volatile abundance ratios are not matching those of any known chondritic meteorites. Okay, if that is the case, late veneer addition definitely could have contributed some volatiles, but cannot possibly be the major source of volatiles in the bulk silicate reservoirs. So the second would be, probing whether atmospheric loss is an important part. Well, for atmospheric blow off to play a major role in setting the bulk silicate earth, the volatile ratios or the volatile abundances, we kind of need to get a sense of what type of atmospheric composition would be reasonable in equilibrium with the magma ocean, or in equilibrium with the molten silicate at the surface. So in order to generate this superchondritic carbon to nitrogen ratio, subchondritic carbon to hydrogen ratio, and chondritic carbon to sulfur ratio, we need the atmospheric composition such that it would be more nitrogen rich relative to carbon. So meaning the atmosphere should have a lower carbon to nitrogen ratio. The atmosphere should have similar carbon to sulfur abundance, and the atmosphere should have higher carbon to hydrogen or high carbon to hydrogen ratios, right? So in order for all of these to be true, we kind of expect, or we kind of need the silicate melt solubility that is complementary, meaning silicate melt should be dissolving more carbon than nitrogen, should be dissolving less carbon than hydrogen, and so on, in order to support an atmosphere that is complementary in its composition. Okay, so we need to then see what type of solubility data we have. Can we support this? So this is a quick plot. Sorry, this is a busy plot, so don't worry about all the details here. But roughly, I'll ask you to pay attention to what is the solubility of carbon in the silicate melt as a function of oxygen fugacity. So this is going from IW to much more reducing conditions. So roughly IW -1 to IW. These are the conditions where we think core formation took place or magma ocean crystallization eventually took place. What you can see is under these conditions, carbon dissolves in the silicate magma in the order of hundreds of ppm at best, maybe approaching 1,000 ppm, no more than that. We understand how it dissolves. Chiefly it dissolves as carbonate or carbon monoxides at these type of conditions. It dissolves as methane under these type of conditions. But bottom line, it dissolves no more than hundreds of ppm, okay, in the silicate melt. In contrast, what Daman Grewal's experiments have showed, and several other groups around the world that are cited here, that nitrogen in these reduced silicate melts can dissolve in much higher abundance. What you can see here, these are not exactly solubility experiments. Solubility experiments would give you even higher abundance of nitrogen. But what you can see under similarly reducing conditions of IW -1, IW -1.5, and so on, nitrogen content in the silicate melt can be in the order of 8%, right? In comparison to hundreds to 1,000 ppm, nitrogen concentration is actually much, much higher, right? So what that means is nitrogen solubility in the silicate melt is much greater than carbon solubility in silicate melt at reducing conditions. Sulfur, I am not showing you guys here today, but you can take my word for it. The sulfur solubility in the silicate melt is similarly much higher than that of carbon solubility in silicate melt at reducing conditions. So if atmospheric blow-off was one of the major contributors in setting the relative abundances of major volatiles in the bulk silicate earth, atmospheric blow-off would leave a silicate magma ocean that is subchondritic in carbon-nitrogen ratio and subchondritic in carbon-sulfur ratio. But that is not what we see. We see bulk silicate earth having a superchondritic carbon-nitrogen ratio and a chondritic carbon-sulfur ratio. So what does that tell us? That tells us lead veneer addition was probably not one of the major contributors, and atmospheric loss was also not one of the major contributors. So that brings us to the third thing, whether or not core-mantle fractionation was a major player in setting these abundances. So this is one aspect we have been focusing a lot on over the last almost 10 years now. Again, trying to figure out what is the nature of carbon partitioning during core formation, meaning what is the nature of metal to silicate or alloy to silicate partitioning of carbon, how much carbon went to the core during the formation of our planet, and how much carbon stayed behind in the silicate portion of our planet. So again, this is just one plot. Again, plotting now, instead of solubility, I'm plotting this carbon partition coefficient, meaning concentration of carbon in the alloy divided by the concentration of carbon in the silicate. So these numbers basically mean if this number is greater than 1, it basically says carbon is siderophile element, meaning carbon is going to the core preferentially. If these numbers are less than 1, then you know that element is a lithophile element, or meaning it's not preferentially going into the core, it's preferentially going into the silicate. What you can see plotted as a function of, again, oxygen fugacity, the partition coefficients of carbon. Again, there is a lot of different aspects how carbon partition coefficient is affected. They are listed here. But roughly speaking, partitioning of carbon between alloy and silicate, the numbers are in the order of several hundreds to thousands, meaning carbon is an extremely siderophile element during core formation conditions, right? And this can be explained by the fact that propensity of carbon entering into a metallic phase, which we already knew from metallurgy data from a long time ago, is much higher than propensity of carbon going into a silicate melt, especially under reducing condition, things that I showed you guys before. So carbon is extremely siderophile, but then we need to not only know the metallicity or metallic behavior of, or metal affinity of carbon, but we also need to know similar affinity of other important life essential volatile elements if we need to explain these relative abundances. So we did similar experiments figuring out the partition coefficient of sulfur in this case, again, between metal and silicate. What you can see is sulfur is also siderophile. However, take a note of these numbers. Sulfur is siderophile, but sulfur's partition coefficient between alloy and silicate is in the order of 10 to 100 at best, okay? Whereas carbon, again, I'll remind you, was in the order of hundreds to 1,000. So if you plot the carbon partition coefficient divided by sulfur partition coefficient, what you can see that dC over ds, this ratio is always much greater than 1. So in other words, carbon's metal affinity is much greater than sulfur's metal affinity. So if you have equilibrium core formation, meaning if molten silicate and molten alloy equilibrated and carbon and sulfur both participated in that fractionation process, the carbon to sulfur ratio of the bulk silicate earth should be lower than the carbon to sulfur ratio of chondrite, meaning carbon to sulfur ratio will become will get modified in the process, right? Will become subchondritic, but that's not what we see. Bulk silicate earth carbon to sulfur ratio is chondritic. So if these volatile elements were present during core formation, then we have a problem. We will not be able to explain the bulk silicate earth abundance this way. We also wanted to look at nitrogen, whether on what constraint nitrogen provides in this type of a story. So relatively recently, again, Daman Grewal led charge in figuring out nitrogen partitioning behavior during core formation. What is shown here is, again, the partition coefficient of nitrogen between alloy and silicate plotted as a function of oxygen fugacity. These are experiments conducted over a range of pressure, range of temperatures mentioned here. What we see here is nitrogen's behavior is somewhat interesting. At relatively oxidizing condition, nitrogen is actually acting in a siderophile manner, meaning it loves to go into the metallic phase or into the core more than it loves to stay in the silicate fraction. However, when you go to much more reducing condition, then nitrogen can possibly become a lithophile element if under graphite saturated conditions. But nonetheless, nitrogen, even if it's siderophile at oxidizing conditions, if you look at the numbers, these DEN numbers, they are in the order of like 10 or anywhere between 1 to 10, okay? So much lower than the partitioning coefficient of carbon. What that means is, again, if you play the same game as we kind of played with partitioning of carbon relative to sulfur, if we plot now partitioning of carbon relative to nitrogen, this DC-DN ratio, as you can see that under all oxygen fugacity conditions that are potentially relevant for magma ocean differentiation and metal separation from the silicates, carbon is acting in a more siderophile manner than that of nitrogen. So that means equilibrium core-mantle fractionation should make the bulk silicate carbon nitrogen ratio for our planet much lower than that of chondrite. But again, I'll remind you, it's exactly opposite to what we see or what we estimate for the bulk silicate earth estimate. CN ratio of bulk silicate earth is superchondritic, not subchondritic, right? So that means clearly equilibrium core formation is also going to pose a problem if we want to explain the bulk silicate earth abundance of these major volatiles. Hydrogen, behavior of hydrogen, this is something that we have not explored in our lab directly yet. There have been few studies around the globe which kind of try to tackle this, meaning partitioning of hydrogen between metals and silicates. There seem to be some contradiction across different groups, but bottom line, it looks like currently that hydrogen is mildly lithophile, or maybe it becomes slightly siderophile if you go to higher pressure, but effectively hydrogen doesn't seem to prefer metals over silicates or prefer silicates over metals one way or the other tremendously. It's kind of hovering around that D of 1. So what we can do now is, just to summarize what we kind of went through, is we can use all of these partition coefficients that we determined for carbon, for nitrogen, for sulfur, and others have done it for hydrogen. We can parameterize them as a function of many different intensive and extensive variables that seem to influence them. And then we can forward model what type of bulk silicate earth elemental abundances and elemental ratios for these major volatiles we will predict if we allow equilibrium core formation and atmospheric blow off to take place, right? So because we know there is an FO2 gradient potentially in the protoplanetary disk going from the central star or the sun away, we can take into account growth of planets in different zones and at more reducing conditions, less reducing conditions, and so on and so forth. So that's what this slide does, or tries to do at least. What it does, or what it's showing between the two panels, the left and the right. The left panel is the modeled abundance of these elements, carbon, nitrogen, sulfur, and hydrogen, in the bulk silicate earth normalized by CI chondrite. And the panel to the right is showing the similar abundances of those major volatiles, again in the bulk silicate earth normalized by chondrite, but in this case, not just affected by core formation, but by core formation as well as that equilibrium atmospheric composition being lost by some sort of an atmospheric blow off. And different curves are showing different extent of alloy silicate equilibration. So in this case, there is almost no equilibration between the core and the mantle as the core formation took place, which we don't think is perfectly realistic. But then this black curve is showing 100% equilibration between the alloy and silicate, and that may not also be perfectly realistic. The reality may be somewhere in between, where metal and silicate equilibrated to some extent, but not completely, right? But what you see is, based on our experimental data and parameterization of those data, we would predict in both of these cases, we would predict or produce a silicate reservoir that is extremely depleted in carbon, followed by nitrogen, followed by sulfur and hydrogen, right? But if I compare this elemental abundance pattern for major volatiles with the one that is estimated for the present day bulk silicate earth, which is that red curve here, you see that none of these models actually produce the elemental abundance pattern, and especially the relative abundance pattern between these different elements. So clearly, as we kind of set out to kind of probe different processes, we ruled out lead linear addition, we kind of ruled out atmospheric loss, but now based on what I just showed you, I would also like to rule out core-mantle fractionation as a process that, at least equilibrium core-mantle fractionation process in our own planet as being a major player in setting these elemental abundances. So this slide looks pretty grim, right? Because I set out with 3 possible hypotheses, but now I kind of have ruled out all of them as being the major players. So clearly there is a roadblock here. So then we started thinking, what could be some of the ways that we could get around these potential challenges? One of the things then we considered that, given the fact a large planet like ours not only grew by accretion of undifferentiated bodies, but it also grew by collisions with large differentiated bodies, like different size planetary embryos and asteroids and so on. There is now then the opportunity, the Earth then had the opportunity to sample compositional heterogeneity in the disk. So meaning it could accrete a protoplanet or a planetary embryo that sourced materials from different parts of the disk, and accordingly may have had a very different chemistry of the core and quite a different chemistry of its mantle itself. So we started to take into account growth of Earth via giant impacts, right? So once we do that, now we open up the possibility of the core composition deviate from pure iron alloy, but much more, an alloy with quite a bit of different chemistry potentially. And interestingly, what we started to realize that indeed, if the sulfur content of the alloy or the silicon content of the alloy, meaning the composition of the core, if they start to deviate from 0% sulfur or 0% silicon, if you have much more sulfur in the core or much more silicon in the core, the solubility of carbon in the alloy melt actually diminishes strongly, okay? These are no surprise, by the way. Again, the metallurgy data already was hinting at this based on experiments and thermodynamic models at ambient conditions, or meaning at 1 atmosphere. But we then subsequently did higher pressure experiments, which kind of strengthened all those previous metallurgy data, that indeed the solubility of carbon in the alloy drops quite a bit as a function of sulfur content of the alloy and silicon content of the alloy. So if this is the case, now we have the possibility of enriching the carbon in the rocky portions of the planetary reservoirs through expulsion of carbon from the core. Why? Because the limit to which carbon can enter the core now can be set at a fairly low value, depending on the sulfur abundance of the core or the silicon abundance of the core, right? The carbon, which was otherwise a very siderophile element in all our previous experiments and models, as I argued, may not be able to be that siderophile, because there will be a limit set by sulfur content of the alloy or silicon content of the alloy. And any excess carbon will then be expelled from the core and will float as graphite, flotation, crust, and so on, and contribute to the silicate reservoirs, right? So we kind of wanted to expand on this hypothesis, and we did further experiments in a mixed volatile system, meaning in metal silicate systems that had carbon, nitrogen, sulfur, all of them. And we wanted to explore how the partitioning of carbon relative to nitrogen, or how the partitioning of carbon relative to sulfur vary as a function of, for example, sulfur content of the core composition or sulfur content of the alloy melt. And as it turns out, very interestingly, this DC-DN ratio was much greater than 1 in a sulfur poor environment, but in a sulfur rich environment, this DC-DN ratio ends up being less than 1. Similarly, this DC-DS ratio again was much greater than 1 in sulfur poor environment, but when the composition of the core is very sulfur rich, the DC-DS ratio again ends up plotting much less than 1, meaning the siderophile affinity of carbon relative to nitrogen and sulfur diminishes quite a bit and actually flips when you allow the composition of the core to be quite different. So once we showed that, we then could establish that if you have a planetary embryo that has a very, very sulfur-rich core, you can get around this problem of greater affinity of carbon towards the metal. You can change the CN and CS ratio to act in quite a bit of a different way than what we were getting in sort of more garden variety scenario of core formation, with the composition of the core being set to what we expect for our own planet. So once we establish that, what we set out to do is we set up an inverse Monte Carlo simulations where we said, okay, given we can now create a planetary embryo with a sulfur-rich core, whose mantle or the silicate reservoirs can have the right attributes, very, very similar to what we see in our bulk silicate earth, can we figure out, or can we compute or estimate what is the composition of the impactor and what is the mass of the impactor that we need such that we can explain the bulk silicate earth abundance? So what were some of the known things? The known things were the carbon, nitrogen, and sulfur abundance in bulk silicate earth, and these ratios were known. The variables, these variables were known from our experimental parameterizations, but these were our unknowns. In doing so, what we got is very, very interesting. So all of these color shaded regions are showing you guys the solution space that can satisfy the bulk silicate earth carbon, nitrogen, and sulfur abundance and the abundance ratios. So what you see is if the size of the impactor is somewhere between 5 to 10% of the size of the present day size of our planet, if the bulk carbon budget of that impactor is somewhere between 1,000 or maybe 2,000-3,000 ppm, we can satisfy the bulk silicate earth abundance of the major volatiles by merging a planetesimal or a planetary embryo having that size. So very similar to a Mars-sized planetary embryo that has a sulfur-rich core. If we allow that type of planet to merge in a late growth stage, we can satisfy, or we can achieve the bulk silicate earth abundance ratio. So based on that, we kind of came up with this model, again, led by my current student, Daman Grewal, that was published last year, that first there was a formation of a Mars-sized planetary embryo that had a sulfur-rich core. Having this core to be sulfur-rich allowed the silicate portion of this planetary embryo to gain carbon through expulsion of carbon from its core. But then at the late stage of growth of the proto-Earth, if this particular planetary embryo merged in a near perfect manner with the protoplanet, and if the core more or less merged with the core and the silicate portion mixed in with the silicate portion, then you can explain the chondritic carbon to sulfur ratio, superchondritic carbon to nitrogen ratio that we see in our own planet. So what this is basically calling for is potentially even the moon forming impact itself, providing the major delivery of the volatiles and actually establishing the volatile element ratios that we see in the present day bulk silicate plus atmospheric portion of our planet. So this study accordingly gained a lot of, I guess, public attention because it kind of suggested that potentially the moon forming impact was responsible indirectly for the origin of life. Of course, the moon forming impact itself did not, make the case for origin of life. What it did potentially is to deliver all the life essential ingredients, especially carbon, nitrogen, and sulfur, that eventually was necessary for origin of life. So many of these papers ended up covering it. So if I can take maybe the last 4 to 5 minutes, one more thing I'll kind of touch on is one additional thing these type of experiments allow us to do is to also probe planetary differentiation processes, and in particular, the volatile element fractionation during these planetary differentiation processes between two types of distinct planetary differentiation scenario. One, where the planetary differentiation was an internal process, meaning there was an undifferentiated shell. We think many of the chondrites kind of originate from undifferentiated shell of parent bodies, but there could be internal differentiation, meaning there could be core formation internally, although there is no communication with the proto-atmosphere and the silicate magma ocean if the magma ocean is internal in this case. But in many planetary embryos and large planets like ours, we think the magma ocean was external. In other words, there was the magma ocean was actually had a surface, and accordingly there was interaction of the magma ocean with the proto-atmosphere. So what our experiments then allow us to do is to figure out what type of atmospheric chemistry is predicted based on what is the abundance of these elements we see in the silicate melts in our experiments, and not only just the abundance, but what type of elements we can constrain from our experiments. So this is something I already kind of showed you guys, like that at reducing conditions that is relevant for a magma ocean or core forming magma ocean. In particular, carbon solubility in the silicate melt is low, nitrogen solubility in the silicate melt is high. We kind of already talked about these, but one thing in addition we are constraining from these experiments, and this is one paper that was published earlier this year, again led by my current student Daman Grewal, is we can do spectroscopy, specifically infrared spectroscopy and Raman spectroscopy of these experimentally generated glasses to try to see how carbon, nitrogen, hydrogen actually was dissolving at these high pressures and temperatures. So these are some raw IR spectra generated from 3 GPa, 1800 degrees C. Different curves are at different oxygen fugacity, so going from relatively less reduced to more reduced conditions. And these are now background corrected. What you can see is from these type of spectroscopy, if you are not familiar, these different peaks call for different modes of volatile dissolution. So for example, in this case, we are predicting NH stretching. So there was some modes of dissolution of nitrogen-hydrogen species. Here, this is either calling for a CO, C triple bond O dissolution, or maybe a cyanide type of dissolution or CN dissolution. These two bands in particular are calling for dissolution of nitrogen in the form of esters or primary or secondary amide. And this particular peak right here is calling for dissolution of carbonate, dissolution of carbon in the form of carbonate. What's important here is to see that the peaks actually change in their intensity as you go from less reduced to more reduced conditions. So what that tells you is, as a function of redox state of the magma ocean, the dissolution of volatiles is expected to vary. Okay, this is known for a long time, but kind of for the first time we are getting most realistic mixed volatile system data in terms of spectroscopy. So if we go kind of little deeper, and I know this is kind of getting maybe a little too technical, but what this plot is now showing you from a plot like the previous one, we can now calculate how the relative contributions of different dissolution is changing as a function of oxygen fugacity and as a function of temperature and pressure. So based on that, without going into too much detail here, what the summary cartoon I'll put here, what we have put out is, if you had an external magma ocean, meaning if there was a communication between the core forming alloy with the silicate melt and the proto-atmosphere with the silicate melt, as a function of the redox state of the magma ocean, you could expect the first primary volatile gases that will be stabilized in the atmosphere to vary as a function of redox. So in the very reducing conditions, you will get ammonia and methane. In kind of intermediate type of oxygen fugacity conditions relevant for Mars, the Moon, Vesta, or Angerite parent body, you will probably get ammonia, CO, and H2O. And then at the final stage of Earth's growth, you will probably get things like HCN or CO2 and H2O and so on. So with that, I'll kind of wrap up and put out the summary slides for you guys to look at. Again, it just says that the major volatiles likely were available throughout the growth history of protoplanets in our in our own solar system. And the silicate fractions and the surface of rocky planets likely acquired very different C and H and S budgets based on the conditions of accretion and differentiation. And equilibrium core formation under reducing conditions actually is known to deplete the silicate portion of the planet differentially with respect to carbon, sulfur, and nitrogen. Carbon should be depleted most, followed by sulfur, and followed by nitrogen. And the terrestrial carbon, hydrogen, nitrogen, and sulfur budget actually cannot be explained by equilibrium core formation or atmospheric loss or gain if you are doing this type of processing in our planet with the composition of the core as we kind of estimate it to be. However, for explaining the volatile budgets or origin of volatiles in our own planet, we can call for, or we can take into account, the protracted growth history. And accordingly, our planet had the opportunity to acquire these volatile elements through acquisition and merger of a differentiated body, such as the moon forming impact, Theia, for example, where if those bodies had a very different core composition, the core-mantle fractionation in those type of bodies could have been quite different than what we would have expected for our own planet. And accordingly, merger of that type of a body with our own planet could potentially contribute in a very positive way the actual abundance pattern that we see, and probably was one of the major contributors of volatiles in our planet. With that, I guess I will stop and can take questions, and I'll give a quick shout out to our Clever Planets team and the website and the Twitter handle for that. Thanks.
Great. Thank you very much, Raj, for that great talk. Please feel free to turn on your mic and applaud, or send him some applause emojis. I'll do mine from here, at least representing all of you. So thank you again. So we definitely have time for a few questions. So like I said at the start of the seminar, if you have a question, I'd like to ask you to raise your virtual hand, and then I will call on you and ask you to turn on your video so that you two can speak directly to each other. So first hand up I see is Mike Wong.
Hi, Raj. That was an excellent talk. Thank you for that. Yeah, so I guess my question is about comparing Earth to Venus and Mars, because Venus and Mars didn't have a large late moon forming impact as far as we know. But they still have these volatile elements on them. We've found organics on Mars. Venus has lots of carbon in its CO2 atmosphere. So I guess how can you test this theory that we needed a large Mars-sized object that was differentiated to have delivered all of our volatiles?
Yeah, that's a great question, Michael. Thanks for asking. So for Mars, one thing we know that one thing that's different between Earth and Mars, again, based on sort of siderophile element geochemistry and partitioning behavior, what we have, not we, like the community has developed over the years. One thing we know that sort of this core forming magma ocean condition for our own planet likely evolved quite a bit, meaning it started out potentially very reduced and then eventually got oxidized, or some people argue that it started oxidized and eventually got reduced. But bottom line being, there likely was as much as 4 or 5 log units different in terms of oxygen fugacity during the subsequent stages of core-mantle equilibration. Whereas for Mars, I think the estimated conditions of core-mantle equilibration is much more oxidized. Well, it's still, of course, metal was forming, clearly you have a core, but it's kind of like IW-1 or something like that, rather than IW-2, -3. So one is that, and accordingly, kind of in a simple, in a very simplistic core-mantle equilibration type of model, I would expect more carbon in the silicate portion of Mars compared to the silicate portion of Earth. Of course, for Earth, we are specifically calling for a very different paradigm in getting these volatiles. But if both were forming by sort of more normal core formation scenario, equilibrium core formation scenario, the parameter space would actually allow Mars's silicate fraction to have higher abundance of carbon compared to that of Earth. So that's one. Okay. For Venus, that's, of course, I mean, I wish I knew the answer, but partly because, I mean, I hesitate to say one way or another. And you may be right that Venus actually poses a challenge for this model. But on the other hand, I would also argue, I think we know so little in terms of the core formation condition of Venus that I would hesitate to predict one way or another which way it would go. But it's possible, like if it didn't grow, it may not have grown by the giant impacts, but the question would be, did Venus have this evolving magma ocean conditions, which, you know, it's anybody's guess at this point, that, right? Like maybe it did, maybe it didn't. So yeah, clearly it's possible that there were some sort of, but again, the current budget of a very CO2 rich atmosphere in Venus may not necessarily be linked directly to this early stage of planetary differentiation, right? Because the one thing I did not talk about, that's something we do care a lot about in our research, and you'll have to get me back for it for another presentation perhaps, but sort of partial melting and secondary volcanism, right? Like the degassing process from a solid mantle. Like that may be one place where Venus and our own planet diverged, not so much in terms of the initial inventory of volatile elements, but how massively CO2 rich atmosphere was potentially developed by outgassing, and whether or not why that was not developed in our planet, or maybe it was developed but our planet had plate tectonics kicking in very early and accordingly had mechanisms to sequester that CO2 away through weathering as well as subduction. So there may be other later processes that potentially explain this bifurcation that you were referring to between Venus and Earth. I'm not necessarily sure that there has to be a big difference in terms of these volatile budgets between Venus and Earth right from the get-go, which is the focus of this talk. I don't know whether I answered it. Yeah.
All right, great. Thank you. Next hand up is David Catling.
Hi, Raj.
Hey, David.
I actually have three questions. Hopefully they can be answered briefly. So in your overview diagram, like on the left side, you had Mercury, and I guess Mercury ends up reduced because of its size and it's very small. And you had like a lot of methane in the atmosphere. But if it's so reduced, why isn't the melt carbon saturated, and would a lot of methane actually get out? And then secondly, with this question, this is still the first question, wouldn't such a small body just lose a lot of atmosphere anyway from this, like Mercury did, although it's close to the sun? That's another factor.
Yeah, great. Both are great questions. Yeah, so what we are predicting is not so much what we expect the equilibrium final atmosphere to be. What we are predicting here in this cartoon is what is the initial gas composition should be. But you are absolutely right. One thing again, just because I was trying to wrap up, I did not point. Now your question allowed me to now focus this. What these black specks here in this diagram are supposed to refer to is the fact that because it's so reduced, the silicate magma ocean would actually get graphite saturated. Which is basically, I think, what you were referring to. And accordingly, not a lot of outgassing can take place. But whatever outgassing will be, the species should be a reduced species. But that's not to say that there will be a lot of outgassing. All I'm saying is the equilibrium species, if you have a little bit of hydrogen, should be methane rather than CO2 or CO. But you are absolutely right. The most of it is actually expected to be sequestered. And actually from the MESSENGER mission, there are some evidence that Mercury likely had a primary graphite flotation crust, which is now overlain by secondary silicate crust. So in all the places where there are impacts, the spectra is suggesting that graphite is getting excavated, and our experiments would be perfectly in line with like original graphite flotation crust in Mercury, suggesting that most of the carbon actually did not degas. And the core was actually getting carbon saturated and was getting expelled from the core, and accordingly that flotation crust formed. But you are absolutely right, the methane abundance in the atmosphere will be very low, but I'll still say that whatever the species is, it should be methane. And yes, absolutely, given it's a small body, it probably would be lost. So I'm not trying to suggest through this diagram that we expect a methane or ammonia rich atmosphere for Mercury, but initial outgassing should give you those species.
Okay, well, yeah, thanks. That's really interesting. And then the second thing, you showed iron meteorites at some point, which was like the nitrogen isotope ratio. But But is there a lot more that you could glean from iron meteorites, ones which have come from differentiated bodies that you could, I don't know whether they were big, any of them were big enough to have a magma ocean, but would looking at iron meteorites be a way to test, not just with nitrogen, but with other elements, to test parts of your metal silicate partitioning ideas? Because those are real bodies that differentiated.
Absolutely, and you are on one hand, I don't want to give too many answers because these are like a couple of works that are in the pipeline or in progress, but exactly that's what we are doing. We are trying to test, you're absolutely right, these are differentiated bodies. We have the cores basically, right? We have the cores from these bodies where we can measure both the elemental abundances of these volatiles and the isotopes. So one thing we are trying to do is to probe the volatile abundances of these iron meteorites and try to predict what type of differentiation regime that these bodies underwent, specifically this internal versus external type of magma ocean scenario, and what can explain their abundances. Of course, there are some unknowns in terms of like the size of the parent bodies of these iron meteorites. There are some ranges, but they are much smaller than, so we initially set out to do these for, Mars-sized bodies or shallow magma ocean of our planet. For iron meteorite parent bodies, we are probably talking about conditions that are actually more modest than our experiments. So there needs to be some, parameterization and stuff that needs to go in. But no, that's exactly where we are heading. That we are trying to use them as some sort of a benchmark and try to see if we can explain them.
Okay, and then my third and final question is: there must be many planets out there currently which have magma oceans, right? And so these would be things like sub-Neptunes with really thick hydrogen envelopes where it's so hot on the surface that it has a magma ocean or something. Have you thought about looking in the future or projecting forward and saying, well, these, we could look for these kind of chemistries in these exoplanet atmospheres, and that might help understand the magma ocean?
Yeah, no, that's exactly where we should be heading. We haven't specifically written, using the term, maybe exoplanet with this redox condition or exoplanet with that redox condition, but that's basically what this, I would like whoever out there in this audience, whoever is interested in the exoplanetary differentiation and magma ocean processes in exoplanets, this diagram, although pretty simplistic and kind of geared towards our own solar system bodies, but this is exactly what this diagram is supposed to be doing, right?
You need to get bigger.
Right. So yeah, absolutely. So and this is something I was telling some of the students when I met earlier, some aspects of our speciation information and so on are transportable to exoplanetary systems if the bodies are small enough. But then we are talking about if we are talking about super Earths or sub-Neptunes, then we are talking about very different regimes of solubility and so on. And then some of these are extrapolations and could be accordingly wrong, as you know. So yes, absolutely, your point is perfectly well taken. Some of this is transportable and it could be a guide, but would I argue that all of it should apply exactly? No, absolutely not, for exactly the reason you just stated.
Okay, thanks very much.
Yeah, thanks, Dave.
All right, great, thank you. So we've reached past 4 o'clock here in Seattle, so I think we should probably wrap this up. So I want to thank Raj again for a fantastic talk, and if you feel so inclined to unmute and applaud again or give him an emoji, I would encourage you to do so. Hopefully we'll get you up here in Seattle in person sometime, Raj.
Thank you so much. Thank you, everybody.
Yeah, thanks so much again, and we'll see you all at the next seminar. Take care, everyone.
Take care, everyone. Bye-bye.